can get, or to the, your colors keep on.
Yeah.
All right. Well, down in front.
Actually,
Turn on. Yeah. I think John came to the lab in 1984.
That's right.
And at that time we had postdoc interviews done in person. And those I think. I still remember that now. And Don came and hardly anybody else.
The only reason you took me in the end.
No competition. Anyway, all that aside, Don has been a great guy, and it was a joy to have around. And after he finished with us, he spent about 6 months, I think, in Toronto before moving to Germany, where I guess he spent your entire career. He went to Bayreuth first for a number of years, and then moved from Bayreuth to Munich, and climbed up the ladder, did a bit of bureaucracy, spent a couple of years in Brussels, I believe, gave out money to some people in a big way, and back to Bayreuth, where he still is. John's interests are essentially reflected in kind of simple, perhaps obscure title. Has spent his entire career, I'm afraid to say, in some context on magmas, volcanoes, and silicate and rock properties. And there's only very few people who understands how to link properties that in the lab to actual activities in the world, including volcanology, and I believe that's what we're going to talk about today.
Oh, thank you, Bjorn. It's very kind. I'm sure I'm not one of the only few people in the world who can do it, but one of the few people in the world who thinks maybe it's important enough to do. The double-bladed sword, that kind. So, actually, the very first measurements I made, which worked, second year of my PhD, were in Gaithersburg, Maryland, at the National Bureau of Standards, where two gentlemen helped me to measure the viscosity of fluorine-bearing melts with a platinum crucible about as big as this. And a guy who was working with me said, "Dingwell, how old are you?" And I said, "I'm 22. And he said, and he was shocked at my youth. And he said, "Well, I'm going to change my answer." He said, "You might make it." I said, "What do you mean?" He said, "When you retire, you might have had a viscosity model for multi-component chemistry with melts." Dave Blackburn, he was quite a character. Just up the road in Gaithersburg. That was the first time I walked up the hill to the Geophysical lab to meet Hat Yoder. So I've called the talk Experimental Volcanology, Accessing the Inaccessible. Of course, the second part of the title is less informative and more political, but everybody has to sell what they do these days. And I hope that this paradox, accessing the inaccessible, will become clear to you as I walk through what I'm going to tell you. Now, I was here a few years ago, standing in the same place. Many of you might have been there then, and you will see incremental improvements on what I said then, I hope. To start out, when I wrote my own European Research Council grant many years ago, 7.5 years ago now, this is the first diagram I put in. It took me more time than any of the other diagrams in the grant, because I stripped it down to be as simple as I could in order that any Earth system scientist would get it at a glance. That's the whole trick of these hopefully iconic diagrams. Eruptions are the way the lithosphere talks to the atmosphere, hydrosphere, and biosphere on a routine basis, several tens of times per year, and continually and continuously, if you look at the slightly longer time scale, in Earth history. So, of course, with this, I was trying to push volcanic activity into the center of the earth sciences, and not, as often we learn about it, as being a detail on the edge of earth sciences. In fact, when I was educated in Canada, it was more or less pushed to the side. Gold deposits were the real earth sciences, and volcanoes just happened to be responsible for some of them. Okay? And, of course, having Chris Scarf as a PhD supervisor and then coming to the Geophysical lab, I rapidly became interested in the materials that were involved, and ever since then I've been trying to, as Bjorn says, take the material properties and determine them better than before, and trying to apply them to the mechanisms of what's going on when these processes take place. And you know that descriptions of mechanisms can run from the gamut from being lost in details which are of no great relevance for the processes at large. That's one of the paths you shouldn't take, all the way over to saying, well, they blow up, so that's it, that's explosive volcanism, and understanding nothing about the process. And so we're somewhere in between there. I always try to put myself in the middle of things. So I don't need to describe to you the importance of why we do it. It would probably be below all of our intellectual standard for me to claim to you that it's extremely important on a global basis, but it is, and I won't even say anything about this slide. It's also important in ways that we didn't think about much 20 years ago. For example, this diagram which shows the annual forecasted growth in air travel of 5 to 10% on the right-hand side of that diagram all over the globe, and therefore the potential threat due to volcanic ash interacting with jet turbines. And this diagram, which is the causes of death in a volcanic eruption, and you're only supposed to notice that there are many to choose from, and there's even, I think, one there which says other or something like that. So it's an incredibly multi-hazard scenario when a volcano erupts, and yeah, there's lots of reasons to explain to people why we should study it. Of course, we want to understand the volcanoes, as a child might put it. How does a volcano work? And I think, and that's what I've been trying to sell to IAVSE, the Global Association of Volcanologists, that we have a chair or a stool which has 3 legs, which makes it stable. The first is the classical physical volcanology, this exquisite work of describing volcanic deposits, which any of us who study geosciences will have learned a little bit about in our undergraduate education. Geophysical and geochemical monitoring, which is increasingly the big business of volcanology, where all of the money really goes. And then, of course, with the advent of numerical increases in numerical simulation speed, which we've all been sideswiped by or are involved in. There's only 2 ways to be. Theoretical and numerical models. And then this last one, which many people would leave off the diagram. Simply, you won't see this on most people's volcanology talks, by far. I mean, but of course, having been at the Geophysical lab, I stuck it in there. And this is what I'm going to talk about. The last little bit, which most people might even let fall from the table. The monitoring of volcanoes, as I mentioned, is the big business. It's where, rightfully so, most of the money goes in. Because as Ike Kushiro once put to me, you volcanologists have it easy, he said. I said, come on, it's difficult. He said, no, he says, the seismologists have it difficult. They don't know where and they don't know when. You don't know when, but you know where. And actually, Ike's a smart guy, and that's the essence of why it's worth investing in monitoring of volcanoes. You know where. So you can very sensibly put your instruments in the right place with increasing resolution, increasing sophistication, increasing continuity of data transfer in real time, and so on. But what causes all the signals? That's the big crunch, really, of modern volcanology. It's magmatic processes that cause all these signals before an eruption, and then volcanic processes once the eruption is running, right? So in magmatic metrology even, we really have a big advantage these days because we're getting multi-system signals of processes, which are the sounds and the smells and everything else of shallow magmatic processes. So this is a growth area. By far, not all of the volcanic systems of the Earth are hooked up so far. And we have dozens of events per year which we monitor, which are hooked up. It's only going to grow in the future, and there's going to be an avalanche of data. There already is an avalanche of data of various kinds coming in from volcanic monitoring. So, this is my slide in German, where I always joke it's my thank you to the German state for having funded this for a quarter of a century. But basically, it's English is a Germanic language, at least we used to call it that. So you can read most of this. This is saturation, nucleation, growth of bubbles, that one's a little tough, foaming, and fragmentation. And these are, in a model that we don't believe in anymore, a linear succession of events in the physical evolution, some would say the physical degradation of a system, which falls out of equilibrium horribly as things begin to speed up and this machine starts to take over and leaves its magmatic equilibrium or approximate equilibrium state, and everything starts to go south as the eruption runs. So what we try to do in the lab is pick each of these processes apart individually, constrain them, and then sort of in a Frankenstein manner, we try to build the beast again afterwards based upon all the pieces of the autopsies that we've accomplished. And it all started out with a trivial material science idea, absolutely trivial and well known long before I took it and sort of forced its entry into geosciences, which is that the glass transition is behind the explosive eruption of magma. The products of magmatic eruptions are glass shards with a whole bunch of other stuff in them, which are used for all kinds of scientific purposes, which are also a huge environmental problem, so on and so forth. But of course the stuff which is feeding the eruption is quite different. It's a high temperature liquid. And so the transition has clearly taken place between a liquid and a glass. Is it a triviality that we have glass afterwards because it's cold? Or is it more than that? Well, we believed from 1990 onwards that it is more than that. And it is that the transition, the physical transition from a Newtonian liquid to a solid glass is where volcanic ash is produced. So it's actually the transition which you have to look for in order to understand when, under what temperature, pressure, conditions of water content, the explosion is going to take place. And based on that, we could produce a shopping list of all the properties we need to determine where this is, to parameterize where this yellow line is, and we could start playing with it by riding across it, as you'll see in a moment, in the experiments and seeing what happens. For those who have not seen the diagram before, it's just the time scale from fast to slow, so a logarithmic scale of time. And on this scale, it's reciprocal temperature from hot to cold. So you see that it is not an equilibrium feature of these systems. It's a purely kinetic boundary such that time determines its location. Now, this boundary is being crossed all the time, and every time a lava flow comes down a mountain, this boundary is being crossed in a relatively benign way. And here's Etna, and you'll see somebody zip in there and zip out again. There it was. So this is obviously a time-lapse photography. There's another one. If you look at that on one scale of observation, you look at the blocks falling off the front here, it's clearly rocks. But if you defocus your eyes and look at the whole tongue of what's coming down the mountain, then you see something which is moving as a liquid whole. So it's moving from a liquid mass to a solid. In this case, the transition is trivial. It's just where the lava flow will eventually stop, because the amount of solid stuff at the front, through cooling, is enough to hold up the force, the gravitational flow behind it, the liquid. But unfortunately, this transition takes place under very different circumstances as well. And this is a collapse of Unsen Dome. And you have a dome which is also oozing out as a viscous mass,
pyroclastic flow,
and
about
yet
10
it will
times
collapse
bigger than
in the
all
form
that came before.
of solid blocks, which then
Within
explode
moments, it
to produce
overwhelms
this
the valley.
tremendously volumetric ash cloud as this pyroclastic flow runs down the topological talweg, growing as it does, and in the end being cool enough, having sucked in enough air from the sides, that its run out is stopped. If we stay long enough on the video, you'll see that within a second, its advance stops. You can just imagine the kind of native religions that are created around these things across the world in history.
By the time a
How
TV
fickle must
camera in
nature
the
be.
village records this scene, Maurice,
that cloud
Katja,
will
and
stop on
41
a dime
others are dead.
in a minute and just go sideways. And in Indonesia, you have total devastation and total fatality counts 10 meters away from total survival rates. Gods have spoken. So, back in the lab, what we try to do is constrain now everything we need to know in order to be able to put the knowledge of this glass transition into models of the behavior of exploding volcanoes. And the background or the basis of all of it and the way that I fell into it backwards more or less in 1990 was that it all depends on the viscosity. That the viscosity is linearly proportional to that yellow sash, that yellow line you saw going across my conceptual diagram. So we have to determine the viscosity. It's, as you saw in the previous diagram, not a straight line on the Arrhenian plot. And that simple fact that it's curved means, more than a decade of work to get it right, to get all the numbers right. So we have low viscosity data, high viscosity data, very different machines for measuring them, different angles of attack for the relationship between stress and strain rate. Out of it comes, and this is an intermediate result, but it's the best cited version of our model, the log of the viscosity versus reciprocal temperature for the range of chemistry of natural liquids on Earth, total alkalis versus silica. And you see that all these lines are curved. If you match the colors, you see they're all curved with one exception. Nature is curious enough to give us one exception which is not curved, which turns out to be the most explosive kind of volcanism on Earth, which is calc-alkaline rhyolite. That was Newtonian viscosity. It means that the value of viscosity, which is obtained as the ratio of the stress to the strain rate, is constant regardless of the conditions of strain rate. But of course, that's an approximation which fails when you approach the glass transition, which is going to make these liquids solids, which are certainly nothing like a viscous material. And the way they die when they approach the glass transition, which is represented here by this little green arrow, little black arrowhead, is that they collapse in their viscosity. And you may think, well, they're becoming solid. Why did they collapse in their viscosity? That's going the wrong way. The reason they're collapsing is that the structure is dying. The structure is actually being sheared out of its equilibrium state. So that, whereas here you could predict through spectroscopy the equilibrium, structure, distribution, entropy of these liquids, here you no longer can. You're literally taking the atoms and moving them to the wrong place physically, and you're doing it fast enough that they can't snap back. So it's a collapse of the integrity of the material, which leads to defects in the mineralogist sense, and leads to disintegration of these materials. So now I'll take you on two quick trips through the glass transition, and I've simply called them fast and slow. We'll do the fast one first. And the fast one means that we actually create explosions in the lab. And we do it with the help of something that we used to call the fragmentation bomb. We don't call it that anymore in 2017. We call it a fragmentation tank. And what you see here is the atmosphere, which is encapsulated in a stainless steel tank. And at the bottom of it, which you can hardly see here, but is blown up here, you have the magma chamber. And many of you will immediately recognize it as a simple hydrothermal bomb construction, Tuttle and Bowen. So we simply have adapted it for our purposes. And what you see up top is what we call success in this business, which is a big mess, which is ash, which has especially been created and has landed on the bottom plate of this large tank. So we make ash in the lab under controlled conditions of decompression rate, temperature, pressure, pre-existing equilibrium state of the magma. And we do it under conditions which are relevant to dome pressures and temperatures in volcanic eruptions on Earth. And this is just a physical sketch of the experiment. So initially you have air above, bubbly magma below. The bubbles are important, and the bubbles are everywhere in explosively erupting volcanic systems, because the bubbles contain the overpressure in them, which is exposed to a decompressed front above it, and therefore results in a pressure gradient, which may be responded to by further foaming, if it's low enough in viscosity. But in the case where it's too high in viscosity, it cannot respond quickly enough, and the overpressure in the individual bubbles acts upon the walls and literally overrides the tensile strength of the now glass, which is in between them. So I want to show you quickly three results which arise from this work. The first is the threshold, the second is the speed, and the third is permeability influence. What you see in each case is a horribly complicated looking sketch of the hydrothermal bomb, which is below the fragmentation tank. But don't worry about the details of these pictures. Just let me show you a video which demonstrates what happens when these things go up. This is an Unsen dome sample. You can see large phenocrysts which are being torn to pieces together with the rest of it as the decompression wave comes from the top to the bottom. This is taken in a plexiglass tube just so that you can see it. The exact same process takes place at 1,000 degrees inside of a steel bomb with all the same monitors of the progress of the fragmentation. If you do it with something much less viscous, in this case it's analog material, you can get the same thing to happen. And if I speed it up, it just shows one detail of the experiment which is not present on the left, and that is this is still deformable material when it comes down, much more akin to the case, in that case, of a crystal-rich basalt which forms spatter when it hits the ground. Okay? So that's what we're doing. We're blowing them up, but in a controlled way. With the latest videos, you can see a lot more of how it's happening. I hope these videos will work. So with increased resolution of being able to watch these things, we can see what's happening. And now look, you can see some of the interesting complexity of how these things are being pulled to pieces and the complexity which is potentially available in these systems for further fragmentation as the particles which are created collide and so on and so forth. So, and you can see that these are experiments in tubes which are one-way experiments. The tubes are thrown away because they're horribly scored and marked at the end of an experiment. Now we make the ash, and here it is coming out of the top of these experiments. So this is the tank above, waiting for what's coming, and here it comes. Please. Let me click it again. There we go. So this is the gas first escaping, and then behind the gas comes the pyroclastic blast, okay, a directed blast, if you will. Because we high-speed video these things, we can tame the information which is coming out and capture it, and I think we can convince you with these diagrams that although we call it a volcanic explosion, this is a sample which only has a height of about 70 millimeters and a diameter of about 25 millimeters, yet we can have a continuous flow which is coming out of this material, and we can determine the speed, we can determine the deceleration of this event with time, we can even look at individual particles going up and coming down, so on and so forth. So we can begin the science, if you will, of understanding what directed blasts are like in volcanic fragmentation. Now the first major result which is worth mentioning, I think, is how much overpressure do you need in order to cause one of these magmas to fail in this manner? And the answer depends upon one variable and one variable only for at least 90 to 95% of the variability, and that is the bubble content, the porosity. And you can see that it runs down about a factor of 10 from 35 to about 3.5 megapascals. That is the effective dynamic tensile strength of these magmas as they're coming out of volcanic throats. You can also see, to my initial dismay, that it doesn't really matter which magma you put in there. There's a large range of chemistry represented here, that at this point, when it comes to the volcanic explosion, it's not about chemistry anymore, it's about physics, because it's happening so fast that there's no effective role for chemistry left to play at the point of explosion. Before, yes. Afterwards, yes. But at the point of explosion, no. And how fast? The answer is quite slow. These things have acoustic velocities of kilometers per second because we're appealing to them in the rigid state. So they're like any other rock with a particular value of porosity. But the fragmentation speed, the speed with which this column of magma is eroded by this fragmentation due to decompression, falls down to values around 10 meters per second. So that's 100 times less than their acoustic velocities in an intact state. So the fragmentation speed is not the acoustic velocity. It's not the information given to the system that it is decompressing. It is that plus some process which is kicked into action as a result of the decompression based on some characteristic length and probably crack growth and so on, which allows it to proceed at a fairly low speed. In fact, these speeds are so low, they are close to the speeds which are estimated as the high end of ascent speeds for magma, which presents the exciting playing field that there may be a balance between supply and demand, if you will, of the material at the fragmentation event, which may be in equilibrium for a certain period of time. For as long as the volume of the magma being accessed during the eruption is much, much larger than that which is coming through the vent, you can feed this eruption for hours, for days. And this actually happens. We know that explosive eruptions run on and on and on. We call them explosive, but these explosions, quote unquote, are obviously steady state processes which hold for a certain while. I think this may in fact be the key to that. The last point is, and many of you may have been thinking about it, wait a minute, on your plot of porosity, you ran up to 90% porosity. These things must be like, I was going to say Swiss cheese, but it wouldn't be a good example. These things are very open. There must be a permeability associated with this gas phase. How can you use the gas to decompress and explode a solid rock if it can simply leave through its own porous network? And the answer is you can't. You're right if you thought that. But the question arises as to exactly what value of permeability is required for the permeability to be able to compete with or to outrun the alternative of fragmentation. And it turns out that if we look at the PV energy which is in the system, it turns out to be constant up to a certain critical value of permeability for a particular fragmentation threshold, and beyond that it runs away. And this is most simply interpreted as the onset of a permeability which is high enough that the gas gets out and leaves the rocks behind. And of course all these volcanoes are degassing all the time. And as I always joke, you can consider a volcanic eruption, a fragmentation, as basically a industrial accident in a degassing system. The gas has to take the mountain with it sometimes. But it's basically a failure of the degassing efficiency of the system, and the failure kicks in right about here. Let's take a slow walk, and the reasons for doing it are twofold. First of all, when you go slowly, you can measure a lot more stuff. And secondly, there are many systems in nature which go very slowly. The dome-building eruptions. And in fact, it's the collapse and the stability of domes which is one of the greatest themes of living near volcanoes worldwide, because it's these dome collapses which produce most commonly the pyroclastic flows, which are the most deadly things that can happen in the proximal field of a volcanic eruption. So there's three things that we know must be happening as we cross this liquid to solid transition. There must be some viscous heating nearby. There must be the structural effect of the liquid being torn to pieces. And there must be some suspension effect, because we have lots of crystals and bubbles in there which have a physical effect as well on the prediction of the viscosity of the entire bulk of the lava. And so we try to pick these things apart one by one, and I'll just give you examples of one or two of them. We've measured the viscous heating in the system by taking an initial cylindrical sample. In this case, is standard material, an NBS standard glass. I don't think anybody has used this much at one time before. And then deforming it in a uniaxial press, as you see on the left. So you see a slightly barreled sample, very nice and homogeneous, symmetric around its midpoint, which means you have a nice temperature field. It's not distorted. And you see what looks like a very violent thing here, 3 thermocouples which have been placed into drill holes. And we simply deform these things at variable strain rate and look for the onset of viscous heating. We do it with real rocks as well. Of course, with real rocks we have heterogeneity, and you can look at these samples and decide for yourself the degree to which you think we have achieved homogeneous deformation versus heterogeneous deformation. We always try to keep the samples 10 times larger than the largest inclusion. And there you see, and it may sound like a trivial result, it's one that you in principle can predict in theory, but measuring it is a little more difficult at 600 or 700 or 800 degrees Celsius under a deforming system where there's an active temperature control calibrating for any temperature changes in your system, which is the way all of our high temperature controllers work. But you can see that there's a rise in temperature which takes off, but we can measure it already beginning at 0.5 or 1 degree Celsius at 600 to 800 degrees Celsius. And we can actually check those results by looking at the value of the viscosity which results from this, because we're deforming it as we do, and back calculating the temperature change we would need to explain the shift in the viscosity of the sample. And we do, and it works. And you end up with 2 fields which cross each other. You have a proportionality to the strain rate for the structural effect, which is what's destroying these things by fragmentation, which is quite different from that due to the viscous heating effect. So that at the very interesting temperature of about 600 degrees Celsius, which really is relevant to dome lavas, that you can go from a regime where you will hit first the viscous heating effect, and the viscous heating effect will have the effect of pushing you back away from the glass transition, because you've dropped the viscosity. You're more liquid than before, not less. Whereas if you don't do it in that regime, you will hit the blue line first, which is the onset of structural non-Newtonian viscosity, and you will never get to the viscous heating, it will break first. So in rhyolitic lava flows, which we now had the luxury, if I can put it that way, of seeing in Santiaguito, in erupting systems like Chaiten, where we've seen rhyolitic explosion for the first time in centuries, we can actually now argue about where we are with respect to this crossover between viscous heating, which we think may keep some of these rhyolitic lava flows capable of flowing down mountains for months, which they do, versus cooling, which they would otherwise expect to be subjected to. We measure the acoustic emissions in all of it, of course. I say of course because we know that our analog earthquakes, if you will, might have the potential for giving some sort of indicators of failure forecasting methods for anybody at seismology. And so here we have Colima dacite, and we have 3 different values of stress successively in the experiment. Here we have the temperature, and you start to see viscous heating really only taking off in the 3rd part of this diagram. The scale here is difficult for you to see, but that's 1 degree Celsius here. Okay? And here you see the number of acoustic emissions. In other words, small fractures in the material before it disintegrates and stops the experiment. And you see it runs off in a nonlinear way to higher values. And my colleague Jan Lavallee and my colleague Michael Heap are convinced that they can use this to predict volcanic fragmentation events. Of course, at the end we get all the ash. It means we can actually do petrology on the ash, and we can do fractography on the surfaces of the ash. And Tobias Thürig from Würzburg has just done some of this. And what you see is a number of simple phenomena. I will just do a flyby of this right now. But in very simple terms, here we have the fine fraction, and here we have the pressure. And we see that if we increase the pressure, we increase the amount of the fine fraction. So more energy in, the pressure is the energy which is being released during the explosion, more surface created, finer fraction. So the first order, seat of the pants direction of these effects is working quite well. And we do grain size distributions of these things painstakingly with sieving, with laser particle sizing, to make sure that we obtain the total statistical analysis of whether these things are getting finer or more coarse, because in multi-phase materials it can be complex. We look, as I mentioned to you earlier, as a result of the ability to look at high-speed videos in these things, we can also measure the exit velocities as a function of time in the experiments. In this case, very little time, 30 milliseconds here. But we can see clear trends about how these systems decelerate after a certain time past the explosion. And Jacopo Tadeucci and others at Stromboli have done the same experiments by aiming cameras at ballistics, glowing ballistics, which are coming out of Stromboli crater as a result of near-surface explosions. And they also get what looks at first glance as a dog's breakfast, as they would say in England, a big mess over here. But if you pick it apart, you can see it's a superposition of a whole series of trends which show the same time dependence of the speed of ejection of particles. They literally measure individual particles with the image processing, which we see in our experiments. It looks like we're measuring explosions as they occur in these shallow chambers. I'll show you 3 or 4 examples of work in progress, and then I'll end with one little surprise at the end. First of all, I want to show you this diagram from Jan Lavallee's work, now in Liverpool, former student of mine, who is interested in
HBR 3400.
lava in volcanic domes sufficiently that it actually being able to send pathology back. Send so he's using this big device to generate pseudo-tachylides of materials already and then it's if he can reduce the viscous in. And if you've ever walked over a new old dome, one of the first things that will strike you is
now we have to do the very stressful lower velocity.
It's no longer a viscous mass which is flowing in its totality. It has chosen surfaces of weakness, like faults, which come out of the surface of the dome. And you see them very, very clearly, and you can look at slickened sides along the surface, pressure shadows behind crystals and blocks on the surfaces, and they look all the world like tectonic faults. I'm going to say nothing about the role of pseudo-tachylites in tectonic faults. but I'd be happy if somebody else is interested to talk about it later. If these things are breaking, and if the things are still high temperature liquids, will they seal again if we stop moving them? In other words, can there be a cyclicity to all of this, which also might produce its own seismicity? And this is again measurements from Liverpool, where you're cyclically moving up and down two large blocks of volcanic dacite and increasing the contact time, and as a function of increasing the contact time, measuring the force which is needed to pull them apart again. In other words, how do we seal, how do we heal these things? How much time does it take? Volcanic ash could be enough work for all of us for the next 20 years, because volcanic ash is everywhere. It's like any fine material. Once you get it out of the volcano, there's no way to put it back in the box. And it is, with its high surface density, of course, for any process which is proportional to the surface area, a very important element of the Earth system. Mass, tiny. Surface area, enormous. Okay? And this horrible looking diagram, which looks like IPCC, is what they call the life, this is what Paul Iris and Pierre Delmel called the life cycle of volcanic ash. And for sure they've missed a few things. So there's things like aggregation, disaggregation, interaction with all parts of the Earth system, including soil, including life forms, including nutrients falling into the ocean and causing algal blooms. You've probably heard Nature reports about all of this kind of thing. These are all topics for the future. But we, being petrologists and volcanologists, decided let's look at the birth of the ash. What's the first thing that the ash sees when it's born? And the first thing that it sees is this ugly cocktail of volcanic gases which were, a moment before, contained in its bubbles and in some sort of disequilibrium, but not wholly unrelated to the rock around them. But once they are released and that PT path towards this dusty gas going to the surface starts to really kick in, they are horribly out of equilibrium. Their speciation starts to cascade down to what it will be at low temperatures, and they start to attack the surfaces of the volcanic ash again within seconds of the eruption coming out. I call this paradoxical in a recent proposal, and an atmospheric scientist said, don't fund this research. I have no idea why he called it paradoxical. So I should have put in one more sentence saying, well, the volcanic gases came from an equilibrium assemblage with the material they're attacking now in the first place. No chance to do it. So we have built a device which allows us to characteristically and reproducibly allow ash and volcanic gases to talk to each other at high temperature. I have to jump ahead because we're running out of time. This is the sketch of the device. It's basically a tumbler, which is a classic way to react any powder with gases to ensure that there's a reproducibility of exposure of fresh gas ash surfaces to the gas which is flowing through along the axis of the device. And this is the actual beast. There it is in the lab. Sits in a fume hood because we put nasty gas mixtures into this, a lot of them containing sulfur. And you can measure essentially the pickup of the gas components which are later leached out of the materials, and you can see that at very, very high temperatures, at 600 degrees Celsius, you have a take-up or a pickup of a significant amount, for example, of chlorine from HCl, which is used as a gas input, or from SO2, which is used as a source of sulfur in these experiments. And when we wrote the first paper on the results of these works, we thought, who's going to read this paper? Let's use the word sequestration, which of course, as you know, is one of the headlines of global change and carbon capture and so on. So we said volcanic sequestration of sulfur during volcanic eruptions. Right? I mean, obviously in order to challenge people to shake their heads when they would read the title of this paper. Volcanoes obviously don't sequester sulfur, but they do sequester up to half of it. And I've just been reading an article where people are using an argument that just came out, I think, in Nature, which is on the overestimation of the effect of volcanic eruptions on short-term global change. You may have seen this just last week or the week before. And of course, their main argument in this paper is large and small events at a particular volcano show exactly the same signal. But of course, what they're calling large and small events is based on the eruptive volume. And exactly the point we're speaking to here is that the size of the eruptive volume is not one-to-one the estimate of how much SO2, for example, will accompany that eruption. We all know that the rock to sulfur ratio of eruptions varies widely. It's one of the reasons we started doing this. And we think we have a mechanism that might help us to explain why in some eruptions you sequester a lot of sulfur and some very little. And it probably has to do with the residence time in the conduit in those critical tens of seconds before the ash gets out. If you can sequester enough of it on the surfaces of the ash, it just gets dumped down in the valley and doesn't contribute to sulfur in the atmosphere. Okay. Just a word or two about distribution of these ash columns. As you know, it's a huge issue now, predicting ash distribution, almost as important as predicting Chernobyl-type ash distribution patterns. In fact, the original codes for volcanic ash distribution all came from the business of simulating nuclear catastrophic events in the atmosphere. And here you see one example of somebody standing under the ash cloud, Corrado Cimarelli, during the Eyjafjallajökull eruption, famous one that shut down European airspace for over a week. And what you see is particles landing, and you see what happens when they land. They disaggregate. So imagine you're going to the geological record, you're trying to constrain your model of ash dispersion based upon what? Grain size analysis and thickness of deposit. Well, what are the grain size analysis that you're performing? It's not those clumps of ash coming down, which is what counts in terms of the physical model of whether they will stay up or come down. It is the disaggregated stuff which happens when it hits the ground. So this is one of the complexities which is now being built into these models. It's great that there's an active community of simulation of these things that follows every single thing that we do now and tries to build it in. And there is, the latest models have aggregation in them. And disaggregation is being built into them as well. Okay, I will jump ahead. I won't talk anything about the fate of ash when it goes into turbines. That's probably a bridge too far for today, but I will show you this one, if I can get my pointer to the right place. And you know what's coming because you can see the picture of the cover of Geology magazine, but essentially by accident we stumbled onto the fact that these experiments are producing what you can, to all intents and purposes, call near-vent lightning, which almost all volcanoes do when they are in eruption. And so this is an experiment where lightning was not the goal of the experiment, where it was a pure coincidence or serendipitous result that it is ripping away there at the vent. And this has now been analyzed by Corrado Cimarelli. And the turbulence that you see on the edges of this vent appear to be necessary in order for this volcanic lightning to be sustained, which gives us insights into the physical mechanism which creates it. Now you see a more columnar flow, and lo and behold, you see less lightning. And this is the last thing I will say anything about. But once we published those results with those videos, we got an email from San Diego from a former student of Miller who said, "You must do the Miller experiment in your lab." So, of course, when you get a call like that, you go book a plane ticket and fly over and talk to the guy. And that's what I did. And he said, "You have naturally generated lightning, or the closest thing to it. In fact, the entire lightning research community is thrilled that we make it without putting 30,000 volts on two nodes which discharge in a regular way, because doing it in a natural way somehow might give them insights into how natural lightning occurs that they can't get from overkill with lightning labs." So yeah, we all know that there was this old idea that lightning associated with volcanism might be something to do with the prebiotic synthesis of the initial building blocks of life, and some people consider it proven since Miller. We all know that the atmospheric debate about the composition of the atmosphere in the early Earth is intimately linked to this, because Miller was doing it in reducing atmosphere, and some people would, or most people would, challenge this in the meantime. But being people who have the deep breath attitude of experimentalists, we say, let's just do it. Let's do it in atmospheres which are oxidizing. Let's do it in atmospheres which are reducing. Let's proportionally change all the components that we think could be in there and watch what happens. Let's dare to do that before somebody browbeats us back by what they think is the optimal value. And so, in other words, have a field of systematic variations. And all I can tell you today, more nice pictures, is that we have successfully created the first amino acids from these experiments. And I can't say really anything more about it today because nothing is published, nothing is even in abstract form. But basically, we built a new version of our device. We image it here. This is a high-speed camera from the back. That's what it looks like. This is the tank, which you see as a mini version of what we had before. This whole thing is on wheels. The reason it's on wheels is there's a suburban campus of the University of Munich where there's one guy there who spends all day measuring things for the Bundeswehr. He's an explosion expert. He has bunkers in chemistry out in Martins Reed. And you should have seen his face when we went to him and said, would you like to work on the origin of life for a couple of weeks instead of the fragmentation of pig carcasses? He was quite happy to do so. So we are in his lab now, and because it's Germany, we went to a bunker to do this. There you go, safety standards. You're looking through the window, an explosion-proof window, into the device, which is now put in an environment which contains reducing gases as well for the first experiments. So this just a heads up. Most people wouldn't talk about it at this stage in a program, but I don't think anybody's hot on our heels on this one. But we will happily and ignorantly explore the range of potential atmospheric compositions until we see what shakes out of it, and then we'll draw our conclusions. And that's, if you want to understand Don Dingwell, I think that last sentence more or less sums it all up. You know, have the stupidity to just do it, and don't worry too much about people saying it's the most important thing you should be doing in 1986, and not the second most important thing. Don't get too carried away with the bandwagons. So I'll stop right there, and I thank you very much for the patience to listen to that.
Okay. Questions?
Personal video. So I just want to know what happens if can you do similar type of experiment on the waters, and because this is obviously has an implication for
Yeah.
for volcanisms.
Yes, and we're building a big tank to do that. Again, the conventional wisdom for many people would be water. So what? It's very little pressure, so that the basic physics of decompression won't be tweaked too much by the amounts of water that you would see at 1,000 meters, 2,000 meters from Loihi or something like that. But on the other hand, of course, the fate of the particles that come out is a very different fate, because they're chucked into something with a high conductivity and thermal conductivity and so on. So you see phenomena from submarine eruptions of the fragmented material which you do not see under air, largely, such as Limu glass and things like this. And of course, 20 years ago, people would have said, oh, you're going to start working on basaltic eruptions, and they would have been the limit of knowledge at that time. But in the meantime, we know that there are all kinds of calderas at 1,000 or 1,500 meters below the sea floor, so that we have all kinds of intermediate to silicic volcanism also under subregions. So yes, absolutely. Absolutely.
Did you say that dust would be leaving a vent at 10 meters per second in an explosion? I think that's what you said.
In leaving the
Well, if you're
the speed that I
the
talked
speed
about,
of particles leaving a vent, I thought you
hundreds
said
of meters per second.
hundreds of meters.
Yeah, I didn't say it, but the speed that I talked about was the fragmentation front.
All right.
So it's the speed of generation of that front of dusty gas above and porous media below. So the speeds of ejection from vents are well measured from video, and we get them as well, and that's of the order of a few hundred meters per second at the vent base. But of course it's related as well to the depth of the fragmentation front, which may range from, well, it can range from 0 when a dome emerges at the surface and then fragments, but it possibly can go down even to 1 kilometer or more.
I was kind of curious, is there a phreatic effect, with the moist getting caught in chambers and explosive with the water pressure itself blowing things up?
So everything I've shown you is without that effect. But yes, of course, there are phreatic phenomena, and you may know that if you would go with any classical field geologist of the last 20 or 30 years into the field, they would see a fine-grained unit in a succession of pyroclastics, and they will say phreatomagmatic. It was a one-to-one correlation, which is probably horribly oversimplified, but nobody listens to an experimentalist, except you guys. So yes, phreatomagmatic events and phreatic events are on the surface of all of this, an added complexity. And a lady who is running this fragmentation lab with me today, Bettina Choi, has put out a number of papers just in the last 12 months on phreatic explosions, such as on Dake in Japan. If you've seen any of the iPhone videos, most terrifying thing you ever see in your life, where the surface of the planet literally is firing projectiles off like this, and you can hear them pinging like you think you're at Monte Cassino in 1943 or something. So this is a big issue, phreatic events. They are the hard end of understanding volcanism at all, and because they're driven by the collection and the impeding of steam leaving very shallow environments. But it is the same physics, and it just has the added complexity that you have water in the vapor phase, which is failing. And absolutely accessible with these techniques, yes.
Anything else?
Just wanted to, so sequestration, I thought that was extremely surprising result, an interesting one, and a critically important one, was the sequestration of sulfur in these events. How physically or chemically is it sequestered?
Yeah, some of the slides that I jumped by, it's a combination of things, as you might guess, on the surface of these ash. Originally they are ash particles, which are just glass shards with accidental exposure on the surface of any crystalline phase that might be involved in it, right? But of course, when you react these things with the exterior gas, basically two possibilities. There's some diffusive exchange, which is on a very, very fine scale, and I don't want to talk about XPS measurements too much because it's not my favorite thing to do. But we had a lot of arguments about the nature of, and you may know there's a long discussion in the geological literature about the surface of basaltic class and what's really going on, what's diffusing where, and some counterintuitive results. There's the diffusive interaction. This is still 600-700 degrees Celsius. And then, of course, there's the growth of crystalline phases on the surface of the particles, which these are examples of, where you see, for example, the anhydrite growing on it, and then you have the classic reactive growth scenario where you have to try to calculate the transfer through a growing impediment or a growing barrier, like in metamorphic metrology, classic literature. And it depends a little bit on chemistry, which is, of course, what we're trying to argue here. We're still the petrologists on the inside. Chemistry counts. And alkali to calcium ratio counts a lot in the rock.
I thought the volcanic lightning stuff was really interesting. And I was wondering if you could speak a little bit more about that mechanism and how charge is generated and accumulated and discharged.
Yeah, it's highly controversial, but essentially we think that it's turbidity which allows there to be a size sorting so that the fines and the coarse somehow are allowed to separate to an extent that the differential charge between fine and coarse, which exists, so the coarse fragments don't have the same, that's the theory at least, they don't have the same surface charge as the finer material, that this allows a field gradient to be developed such that you can get a discharge through it later. There's also the frictional arguments, the tribological effects which are argued to create charging on the surfaces. We don't think in this expanding flow that that's a major feature. We don't see a lot of evidence for it in our high-speed videos, but complete exclusion, difficult to do. The most exciting thing in the future, I think, of this volcanic lightning story is that as I jumped over, and you might have seen, we're measuring the field, the electric field and the drops in the voltage on the electric field. And the argument is that the amount of discharge which occurs during an eruption may be proportional to the amount of fines which is produced. A rough proxy. Just hope it holds to the one-to-one line over a significant range. And if that's the case, then you might be able to actually determine the flux. You might be able to determine the source function for the entire ash dispersal model that you're trying to cope with in real time by measuring that electric field discharge activity with antennae around a volcanic environment. And that's what Corrado Cimarelli is trying to do in Sakurajima, which thankfully erupts all the time and produces lightning when it does. That would give you the chance that you can monitor remotely the amount of fines coming out of a volcano, albeit through a proxy, and then you would have something which we know changes strikingly. Flux rates from these eruptions, they bang up and down like a system which is between several states of equilibrium. Even lava flow dynamics in Etna will change by a factor of 100% in flux rate when something shifts in the underground. So imagine you're trying to predict in 2 weeks what's over Munich airport, and you don't know if 2 hours ago the flux of fine ash doubled or halved. And it's nighttime, and it's December, and it's Iceland, you know. So you have almost no chance to detect this, although some people with remote sensing are trying to find better ways to detect it. One very elegant way to do it would be if we can argue that these field measurements are a proxy, that the discharge density is a proxy for the fines. If my colleague Corrado was standing here, he would speak for another half an hour on it. I'll spare you that.
All right, Don is here today and tomorrow morning sometime?
I can be.
Okay.
Optional.
Okay, well,
Sure.
in the meantime, it's lunch next door, so those who want to come there, and thanks a lot again.
Thanks a lot. Thank you. Thanks for inviting me.
Yeah.
Give you the, that's even cooler.